Hello everyone. So today what we'll be doing is we'll be solving some of the PYQs and a few of the expected questions for boards 2020 and 5. This lecture definitely you'll see that what all things you can expect for the chapters EMI, atoms, molecules, and nuclei, structure of atom, and dual nature. So let's start quickly. I have selected few of the questions which are your PYQs, as well as I've selected a few other questions as well. So let's try and solve few questions and stay with me so that we can I'll try that I solve each and every question in detail. So let's start with the first question. Come on. So the first question goes: an EMF of 91 millivolt is induced in the windings of a coil. When the current in a nearby coil is increasing at the rate of 1.3 amperes per second, what is the mutual inductance, capital M, of the two coils in millihenry? So definitely, this is one of the most easiest question. All you have to do is you should know the given first. So if I write given over here, we have E with us. E we have is 91 millivolt. So very first thing that you have to do is convert it. So 91 into 10 raised to minus 3 volt. So please make sure that you always remember that you convert each and everything. Conversion is an important key factor. Without conversion, you will definitely lose some of your scores. And this is 1.3 ampere per second. From the unit itself, you come to know that it is nothing but a di by dt. And as you know, the formula for mutual inductance, capital M, is mod E the whole upon mod of di by dt. When I resubstitute things, the value which I get is 91 into 10 raised to minus 3 the whole upon 1.3. By solving this, we get as 17 to 10 raised to minus 3 Henry, or we can also call it as 70 millihenry. And this is nothing but a final answer. So this is one of the most expected questions, and EMI is such a chapter where you will see that at least you will get one question maybe of 2 marks. So such questions you could expect, such easy kind of questions you could expect in your boards. So the next question goes like this. In a biprism experiment, the light of wavelength 5200 angstrom is used to obtain an interference pattern on the screen. The fringe width changes by 1.3 mm, and in this case, when the screen is moved towards a biprism by 50 centimeter, calculate the distance between the two virtual images of the slit. Okay, so as you see, over here, what they are expecting is they are talking about biprism experiment. This question, this was asked last in Feb 2020. Now again, biprism in our syllabus right now, in a new syllabus, there is a very small section of resonance biprism. But if you look at the details, you have many things in it. You have lambda, you have change in fringe width, which is 1.3 mm, and uh, if you know that a detailed biprism experiment, it used convex lenses, which changed capital D. So basically, to approach this kind of question, you have one simple formula: x is lambda capital D by small d. All you have to do is, for such kind of things, just apply the formula that is of change. Okay, so let's try how we can approach this problem. Firstly, I'll write given. For this, you have lambda as 5200 angstrom. You have change in fringe width, which is, I guess, the fringe width changes by 1.3 mm when the screen is moved towards a biprism by 50 centimeter. So the change in fringe width, let's write as x2 minus x1 final minus initial. This will be 1.3 millimeter, and uh, and it is also moved by 50 centimeters. So capital D is also changed. So we'll write D2 minus D1 is nothing but a 50 centimeter. You can also convert it 1.3 into 10 raised to minus 3. And you can also convert 50 centimeter to 0.5 meter. Fine. So all you have is over here, you have only one formula. X is lambda capital D by small d. You have to find small d. So for small d, what you can do is you can approach the same thing like this. Small d would be lambda d2 minus d1. That's it. Write down change in case of your original capital D, write down change in capital D. And in case of original X, write change in X. And just resubstitute the values and quickly you'll get the answer. So 5200 angstrom, so just convert angstrom to meter. And this is nothing but 50 centimeter, which is 0.5. And lastly, you have 1.3 into 10 raised to minus 3. Okay, so by solving, all you get is small d ka value, which is 2 into 10 raised to minus 4 in meter. So this is a distance between the two virtual images of the slit. Fine. So the next question goes like this. The plane wavefront of the light of 6000 angstrom is incident on two slits on a screen perpendicular to the direction of the light rays. If the total separation of 10 bright fringes on the screen is 2 meter away is 20 centimeter, find the distance between the slits. Okay, fine. So this is a really easy question. All these questions are really bonus questions. See, all you have to do is you have lambda, firstly, which is 6000 angstrom, and you can definitely convert it into 6 into 10 raised to minus 7 meter. You have capital D as 2 meter. You have distance between 10 fringes is 2 centimeter. Okay, so all you have is the same type of questions we have solved in our lectures as well. So 10 bright fringe, that is 10 fringes. So 10x ka value you have over here as it is 2 centimeter. So what I can do is I can write the value as 2 into 10 raised to minus 2 meter. So only x will be 2 into 10 raised to minus 3 meter. This is for only one fringe. 10x was for 10 fringes, it was for 2 centimeter, then for one fringe, just divided by 10. That's it. So things get really, really simpler for this. And ultimately, what you have to do is you have to find out small d. Again, you have only one formula for fringe width, which is x is lambda capital D by small d. All you have to do is find distance between the slits, which is small d. Small d would be lambda capital D by x. You have the value for lambda, just resubstitute it. So 6 into 10 raised to minus 7, you have the value for capital D, which is 2 meter. And for x, you have 2 into 10 raised to minus 3. As I said, all these questions are really bonus questions. So the final answer goes 6 into 10 raised to minus 4 meter. So definitely such problems, you have to make sure that you are not leaving this kind of numericals and this kind of problems, because these are definitely bonus questions for you guys. Fine. So next question is, a plane wavefront of light of wavelength 5500 angstrom is incident onto a particular on a slit perpendicular to the direction of light rays. If the total separation, see again the same type of numerical you are getting over here. If the total separation, I guess I've repeated these two questions. No, okay. So again, see, I got confused. See, again, you have 6000 angstrom in this initial question, and the given thing is same. All the given is same. Only thing they have done is just they have changed the wavelength. So I guess this is self-explanatory from this point. So all you have to do is just resubstitute the values. We have solved this question, and this type of numericals are very famous. So you can write 10 raised to minus 8 in meter. You have capital D as 2 meter. You have distance of 10x as 2 centimeter, which is 2 into 10 raised to minus 2 meter, or x is 2 into 10 raised to minus 3 meter. Fine. So all you have to do is, again, you have to find out small d. Again, you have same formula. X is lambda capital D by small d. To find small d, you have lambda capital D by x. Just resubstitute the values, which is 5.5 into 10 raised to minus 8. Or you can write, sorry, I have written 55. So you can write 55 into 10 raised to minus 8 into capital D is 2 meter, and capital X is 2 into 10 raised to minus 3. As I told you that all this kind of numericals, they are bonus for you. So make sure that you are not leaving all this kind of numericals. Definitely, because they are truly very easy questions. Very, very easy questions. You might have noticed that always I'm writing proper given conditions. You might have noticed that I'm not resubstituting the values directly into the formula. First, I'm writing the formula, then the to find thing. I'm getting that to find thing on the left hand side first. and then I'm resubstituting the formula. So I'm not writing more numbers. Okay. So what I'm trying to do is first get your two find thing aside and then resubstitute things. So that would be much easier to understand, much easier to solve, and you also reduce your errors because more the numbers, more will be your error, right? So this is a way that you work with things. Come on. So again, you have one of the similar questions if you notice. So same type of numerical again, and the only thing over here is they have changed the values. So again, a self-explanatory question and very easy question. So we would leave this question here because this is really simple question, and we'll move on to the next question. Fine. So come on. The next question goes, I'll just write over here, same as above. So the next question goes is for dual nature. The photoelectric work function of a metal is 4.2 eV. You have to find out the threshold wavelength. Okay, so as you know, I have given only one general formula for Einstein's, that is your Einstein's photoelectric equation. That is energy is work function plus KE maximum. And this is your golden formula. I have told write energy as H nu or write energy as HC by lambda. You can write work function in terms of H nu naught or work function in terms of HC by lambda naught. Based on your given condition, you can write KE max as EVS, or you can write KE max as half mv square, where V is your velocity and this Vs is your stopping potential. So this cloud is your Einstein's photoelectric equation, and this is one thing that you can apply, you can implement anywhere except De Broglie, obviously. So anywhere in your dual nature. So again, this question might not even require this cloud. Reason being, all you have to do is you have to find out threshold wavelength. So what you can do is you have work function with you. So work function is nothing but 4.2 EV. So just convert it to joule. So this would be 4.2 into 1.6 into 10 raised to minus 19 joule. You have to find out threshold wavelength. So threshold wavelength is nothing but your lambda naught is your to find. And the formula that you have for work function is HC by lambda naught. So just first to find on your left hand side, which would be HC by phi naught. This is both, so we cannot use shortcuts. Okay, so you use shortcuts for your calculations, but while writing, make sure that you are resubstituting each and every value because this is boards and not entrance exam. So for class, I have given many shortcuts, right? I have given value for HC in Joule, I have given value for HC1250 in EV, right? So make sure that you, if you want to solve for accuracy purpose or for fast calculation purpose, what you can do is you can use your shortcuts, but while writing for boards, make sure that you are writing all the steps. So this would be 4.2 into 1.6 into 10 raised to minus 19. So now from here, the things are very, very simple, very, very easier. All you have to do is just calculate things. And the final answer that you get over here is 2.959 into 10 raised to minus 7 meter. Or you can also write it as 2959 angstrom. So this is where the things work. It's very easy problem, bonus question. Similarly, the next question goes in similar manner. The next question is a de Broglie wavelength associated with an electron and proton are same. We have to find ratio of the kinetic energies. So I guess the similar type of question you have, and also you have the given condition over here. The given condition of MP and MPE is also given to you. So de Broglie wavelength, again, you can approach this type of question very, very easily, right? So let's try how you can solve this problem. Just a second. I'm sorry. Just a bit of a glitch. Okay, fine. So I hope these things are visible to you. Okay, so the de Broglie wavelength, let's get back to the question. The de Broglie wavelength associated with electron and proton are same. You have to calculate the ratio of the kinetic energies. See, quite interesting. All you have got is only one information, and you guys know that you know the relationship of your de Broglie wavelength, which is lambda is h by p, h by mv, h by root 2 me, h by root 2 MeV, and for electron we put here 12.27 upon root V angstrom, right? So let's see. The given condition over here is lambda E equals to lambda P, and you have to find out the ratio of the kinetic energies. So the best suitable formula would be this one, right? For lambda. So let's resubstitute things, and to find what we can do is we can resubstitute and cancel out stuff. So the thing over here is H would be root 2 M for electron, energy for electron equals to H upon root of 2 MP EP. Cool. So you can cancel out H, and you can also square on both the sides. So after squaring, you can get MEE equals to twice MP EP. Again, 2 and 2 gets cancelled out. So over here, you can get EE upon EP equals to MP upon ME. And as you know, mass of proton is 1836 times mass of electron. So finally, you can get EE upon EP will be 1836. Great. So this is the way the the calculation goes, and this is the way the things work. Chalo, let's move to the next question. The next question is, an electron is accelerated through a potential difference of 100 volt. You have to calculate the de Broglie wavelength. Very, very easy problem. Feb 23 problem. So let's first write. See, as you know one thing, and that is your shortcut. So shortcut goes lambda is nothing but your 12.27 upon root V, and the final answer will be an angstrom. You have potential difference, right? So all you have to do is 12.27 upon root of 100, which is nothing but 12.27 upon 10, which is 1.227 angstrom or 0.1227 nanometer. So this is the way you can find many things like this, and you can solve many things like this. All you have to do is you have to make sure that you are in your proper senses and your in your proper consciousness, because such easy questions you can definitely fill your pockets with good scores, right? Sure. The next question is, the radius of the third orbit is 0.477 nanometer. You have to calculate the radius of the second Bohr orbit. Okay, fine. As you know, I've given you a shortcut for your radius of your Bohr orbit, and the shortcut is very, very easy, right? Epsilon naught h square upon z by me square, right? And I have also told you that z would be 1 because over here they have not mentioned any other element, so we'll consider it as hydrogen. So again, I can say your radius of the Bohr orbit is proportional to n square, and if it is proportional to n square, all you have to do is you have to find out radius of a second Bohr orbit. So just take ratio R2 upon R3, third Bohr orbit, right? Third Bohr orbit, the radius is given, which will be nothing but 2 square upon 3 square. This will be nothing but 4 by 9. So I can say R2 will be nothing but 4 by 9 times of R3, and you have the value for R3, which is 4 by 9 into 0.477. After calculation, you get the value 0.212 into 10 raised to minus 9 meter, or you can say 0.212 into, or you can simply write 0.212 nanometer. Great. Because the given value will be in angstrom, so you can write it in angstrom as well, or nanometer, or in nanometer as well. Fine. So just remember, I have told you to remember three relations, which is of your radius, your velocity, your you should know the formula for kinetic energy, potential energy, total energy, and binding energy. For relation, you can remember radius, velocity, total energy, and binding energy. This was the same, right? So if you know these things, then all these problems will be really very simple for you guys. Come on. So next is calculate the shortest wavelength of the Paschen series and longest wavelength of the Balmer series. Okay, this we have studied and I have already mentioned. I have given you one table for this, and shortest wavelength and longest wavelength you already know. Shortest wavelength will be always from shortest wavelength will be always from infinity, because shortest wavelength will have more frequency. More frequency means more energy, and longest wavelength will be immediate next orbit of that particular series. If we talk about, for example, Balmer series, so your longest wavelength for a Balmer series will be from third orbit, and for Balmer series the shortest wavelength will be from infinity. So this I have already given. I've given you one good table. Just remember these things. And I've also given a list of shortcuts and a list of the words that you have to find, the techniques that you have to find, and how to approach them. So again, so for the first thing is a shortest wavelength for Paschen series and longest wavelength for Balmer series. So for shortest wavelength, what I can do is you have to show some working. Even if you remember the values, you have to show some working over here. So 1 upon lambda will be R. Paschen series means Lehman-Balmer Paschen third orbit, and shortest wavelength means from infinity. So the shortcut, if you guys remember, this is 9 by RH. So obviously you can resubstitute the value for RH 1.097 into 10 raised to 7, and the final answer that you get over here is 820 nanometer. Again, for longest wavelength for Balmer series, lambda Balmer, for longest wavelength it should be immediate next orbit. So for Balmer series the next orbit is third orbit. So again, if you cross multiply things, you get 36.15 RH, and the final value will be 656.3 nanometer after resubstituting things. So things are quite easier. Things are very, very simple. All you have to do is you have to make sure that just remember the small basic tips and techniques. That's it. Fine. So the next question is calculate the change in angular momentum of an electron when it jumps from third orbit to first orbit in your hydrogen atom. Change in angular momentum. Angular momentum ka formula we already know from a Bohr's second postulate. Angular momentum is nh upon 2 pi. So if you want to find change in angular momentum from third orbit to first orbit, you can simply write nh upon 2 pi. You have to find out the difference. So just do n3 minus n1, and all you have to do is h by 2 pi and 3 minus 1, which will be nothing but h by pi. I think it's boards, so obviously you'll not get such options over there. थोड़ी मेहनत करनी पड़ेगी और एक स्टेप आगे करना पड़ेगा. So L3 minus L1 में ये वैल्यूज सब्स्टिट्यूट करके डिवाइड करके बताना पड़ेगा, and you have to write down the final values as well. So 3.14. So 3 2s are 6, approximately 2.1 something. You will get your final answer minus 34 kg meter square per second. Don't ever forget to write unit. If you forget to write the unit, then definitely they have a scope to give you that question wrong or deduct your marks. And this one final question for you guys. This one type of question which I feel that maybe this was also part of Feb 23, and such questions are not being repeated on a major scale, but I've included here because such same type of questions we have done in class, same type of questions we have done in our module, same type of questions is also there in your textbook. So see, the disintegration rate of a radioactive sample is 10 to the 10 per hour at 20 hours from the start, and it reduces to 5 to 10 to the 9 per hour after 30 hours. And you have to find out the value of decay constant, which is lambda. Okay, so our first rule, let's write given properly. So I'll write in terms of activity over here. So I'll write 81 will be 10 raised to 10 per hour, and only time is 20 hours. This is given to you. And again, 82 is given 5 into 10 raised to 9 per hour. And again, you have T2 is 30 hours, right? And you have to find out lambda. Lambda is your question mark, correct? So if you want to find out lambda, let's solve few things. Let's resubstitute few things. Let's see how we can approach. So step number 1, I have 81. I have the formula for A. I can write AT equals to AO e raised to minus lambda t, the very famous and decay constant ka formula. So what I can do over here is I can write 81 will be AO e raised to minus lambda T1. So when I resubstitute values, I'll get 10 raised to 10 equals to AO e raised to minus 20 lambda. Perfect. Okay, let's name it as equation number 1. Again, I have 82 equals to AO e raised to minus lambda T2. And also I have value of this both sections as well, which is AO e raised to minus 30 e raised to minus 30 lambda. Okay, this is equation number 2. Okay, let's divide equation 1 by equation 2. So when I divide, what I'll be getting over here is 10 raised to 10 upon 5 into 10 raised to 9. And AO will get cancelled, and I'll get over here e raised to minus 20 lambda plus 30 lambda, right? So technically what I'll be getting, the final value will be e raised to 10 lambda, correct? So let's take let's let's put this exponential term on left hand side. So by putting it, I'll get natural log 10 raised to 10 upon 5 into 10 raised to 9 equals to 10 lambda. See, again, I have to convert this natural log, and what I'll be getting over here is log 2. So if you want to convert, yes, definitely we have to convert this natural log to the base 10. So I have to write like this: 2.303 log 2 equals to 10 lambda. See, again, if you notice, I've just formed, I'm just using only one formula, nothing new. And what I'm doing over here is I'm just simplifying things. Okay, so again, I know this value, right? Log 2 and 2.303 to log 2, the final value will be 0.693 equals to 10 lambda. Or definitely, okay, you can directly resubstitute log 2 ka value as well, which is 0.693. And finally, what you will be doing over here is you can find out lambda, which is 0.0693, and the unit will be per hour. So few amazing questions for your revision from this three topics, 3 chapters. Please make sure that you are revising these things very, very well. Just refer our class notes and just refer our small tips and techniques that we have used in our class, and definitely you'll score really very well. So thank you so much, guys. Thank you.